SolidWorks Simulation, Lecture 11, Optimization of a Cantilever Beam. Open a part file. Enter sketch mode. On XY plane, draw a rectangle, 50 by 50. Draw a circle at the center, 20 in diameter. Extrude it into 1 meter long. Save the file on desktop. For CAE analysis, the preparation requires that you load the software here, load the toolbar here, and this is the toolbar, and create a case or static study. First of all, we run a static study as before, and for the second study we'll implement optimization. So now I'll define the material, and I'll copy the library onto customized material, paste it, and then I can change the properties of the material. And the elastic modulus I'll change into 3 times 10 to the 11th and leave the Poisson ratio as 0.3. So I'll choose this material. For the third step, meshing, hide the mesh. Step 4, boundary condition. Loading, surface of loading, direction of the load, magnitude of the load. Run. And for the stress, I need to define the unit and also change the numerical value format into floating point with 4 digits on the decimal, so it is easier to read. 5.0 MPa stress. Also for the displacement, I will change the unit into millimeter and the format of the numerical value into floating point with 4 digits on the decimal point, and it will be 0.216 millimeters. So the reason that I change the unit and format of numerical value is to make it easier to read. So now I'll proceed with the second part of the procedure, which is running a optimization procedure. I'll open a design study, and it will default the optimization. So I'll choose the parameter or variable. The design variable will be the hole, the diameter of the hole. I'll name it D here and choose this dimension. So this dimension will connect or linked to this name. So this will be the design variable, the diameter of the beam. Now I have to set the range because I have declared this variable. Now I have to define the range of the variable. It will be from 20 millimeters to 45 millimeters. So the hole will expand from 20 millimeters into larger holes, and see how the stress and displacement will change. So now I'll have to impose constraints on the system. So I'll add a sensor of simulation data, stress data, von Mises stress with units of MPa, the maximum of the model. The maximum stress will be lower than 6 MPa. Because in the problem we have 5 MPa, so when the hole gets larger, and the stress will be higher, and I'll limit it to 6 MPa and look for a largest hole. And for another constraint, I'll add a sensor of simulation on displacement with total displacement with units of millimeters. The model maximum, the maximum displacement will be less than 0.25. Because in the statics problem I have 0.216 millimeters. So when the hole gets larger, the deflection will be larger also. So I leave it as 0.25 millimeters. So now I have finished with the first two parts. The first part will be design variables. The second part is constraints. And the third part, goal. I'll set the goal as the volume of the beam. So I'll minimize the volume of the beam by increasing the design variable, which is the diameter of the hole. So let the procedure run a maximum diameter for me so that it is under the constraints of stress and displacement and looking for a minimum volume. So now the answer is 34.45 millimeters. And at this time, the stress is 5.8 MPa and the displacement is 0.25. So it is in accordance with the limitation or the constraint we impose on the problem, which is 6 MPa and 0.25 millimeters. So it conforms with my constraint, and expanding the design variable, which is the diameter of the hole, to the maximum value so that the volume of the beam is minimized, and also the mass of the beam or the total material price will be lowest. So this is the very simple optimization problem